So what we've seen so far then is that if you have this function fg, which is a real valued function over the interval ab, and you take some dissection of that interval, and you construct a set of all the possible sums of this form where these ci's and di's are points in the correct subinterval from this dissection of the interval ab, and you take the supremum of that huge great big set of all these possible such sums, then the value of that supremum is the difference between the upper Riemann sum for your function over that dissection and the lower Riemann sum for your function over that dissection. Now we did all of this in this context of functions of this form f times g because that's what we're really interested in. However, everything that we've done would have worked just as well for any old bog standard function. It didn't need to be writable in this form where it's a product of two other functions. So to see this theorem then in its simpler form for a function that's written in a simpler form, consider just the function f that's a real valued function over the interval ab, and consider the dissection d. What does this theorem become? Well, it becomes the supremum of the set of all the sums. Now the sums become a lot simpler now. We've got sum from I is equal to 1 to n, delta xi, that bit's remain the same, but now modulus, and of course we want the function evaluated at ci minus the function evaluated at di, but now the function is written simpler. It's just f of ci minus f of di. So that's what these sums simplify down to when we're expressing the function more simply. Of course, ci and di are still allowed to vary over any value in the relevant subinterval. And of course, here, the upper sum minus the lower sum simplifies as well because we no longer have f times g, it's just f. Now, how can you see that this is still going to hold true from the fact that we know this is true? Well, just set the function g equal to 1. If you set the function g equal to 1, then f times g is just equal to f. So g is 1 for the entire interval ab, hence f times g is just equal to f. So we just replace f times g here with f to get what we've got here. And here, for all of these sums, the g value is just going to be 1 no matter what your choices of ci and di. So those just simplify to 1 and become what we've got here. So that's how you can see that this simpler expression for this same theorem is true from what we've done previously. So actually, when we went about showing this, we were doing it in a very complicated context because of the fact that we are later going to use it in this form. So you might say, well, this is marvellously interesting that these differences between the upper and lower sums can be thought of as the suprema of these sets of sums. But what actual use is this to us? How are we going to use this? Well, of course, we're going to use it in the form that we've got up here, which is why we developed it in this form. And our next move is going to be to find another upper bound for this set. So find another number that is always going to be greater than or equal to every single one of the sums in this set. Why? Because if we find another upper bound for this set, then we know that that other upper bound is greater than or equal to this value because this is the least upper bound, it's the supremum. So it has to be less than or equal to any other upper bound. So by finding other upper bounds, we can actually put a bound on the size of this thing, and we're very interested in bounding the size of this thing because that's what we're trying to do in the Riemann integrability criterion. We're trying to show that we can get this smaller and smaller by choosing clever choices of dissection. So that's our approach then. So we're going to study these sums. So I've pulled out one of these general sums from that set, and we want to take this and try and find something that we're able to conclude is always greater than or equal to the value of this, no matter what our choice of C points and no matter what our choice of D points is. So at the moment we've got one of these general sums from that set. So the first manipulation we're going to make here is actually a bit of a magic trick, and I'm sorry if it seems a little bit unmotivated. So we're going to subtract something off and then immediately add it back again. So I've got the sum from I is equal to 1 to m, which is the same as up here. We've got times delta xi, so that bit hasn't changed. We've then got the mod of f at ci times g at ci, which is exactly the same. But here's the thing that we're subtracting off. We've got f evaluated at ci times g evaluated at di, plus we then add that back again. So we've got f evaluated at ci times g evaluated at di, so that it cancels for every single one of the terms of the sum. And then we've got minus this bit again. So f evaluated at di times g evaluated at di. So hopefully you agree that this is still equal to this. Now, why are we doing this? Well, it's because you can see here we're going to be able to factor out the f of ci and then get a difference of two g's. And then here we're going to be able to factor out the g of di, and then we'll just end up with f at ci minus f at di. And the reason we're doing this is because we're trying to get things just in terms of the function f and the function g, because remember, we know that the function f and the function g are Riemann integrable, and we need to use information that we know just about those individual functions to try and get us some information about the product of the two functions. And this magic trick that we're doing here is trying to split the two functions apart, and it's going to work beautifully, and you'll see how. So the next step is very easy. It's what I've just described to you previously. So we're just going to factor out the common bit. So we've got sum from I is equal to 1 to n of delta xi, then we've got mod, and then from these two terms we've factored out the f evaluated at ci, so we've got f ci times g evaluated at ci minus g evaluated at di, plus, and then here we're going to factor out this g evaluated at di, so we've got g evaluated at di times f evaluated at ci minus f evaluated at di, which comes from this bit. And then we're closing the modulus here. So next what we're going to do is apply the triangle inequality. So to simplify things, let's call this great big thing capital A and this great big thing capital B. Then this modulus bit that we've got here is actually the mod of A plus B. So we're going to use the triangle inequality, which says that this is less than or equal to mod of A plus mod of B. And of course we'll be able to do that for each I is equal to 1 to n. So we'll have n separate inequalities now. Then for each one of those inequalities we can multiply it through by its delta xi, and that delta xi is a positive number, so it won't flip the sign of the inequality. So we'll then still have n inequalities with the delta xi out the front. Then what we'll do is we'll sum all of those inequalities together now. So we'll sum from I is equal to 1 to n, and we're adding all of the things on this side of the inequality together, and then on the other side we're adding all of the things on this side of the inequality together. And because all of these things are less than or equal to the things on this side, when you add all of these ones together, it'll still be less than or equal to all of these things added together. So that's what I've done here. So I'm now concluding that all of this thing is going to be less than or equal to what we've got on this side. So I've split apart the two sums that you would get on this side, because you'd have delta xi times these summed from I is equal to 1 to n, and I've just split those two sums apart so that we've got the sum from I is equal to 1 to n of delta xi times the mod of A, so this bit, plus the sum from I is equal to 1 to n delta xi mod of B, which is this bit. I've also pulled apart A a little bit, so we've got mod of A, but we've got A is a product of two things, and we're using the fact that the modulus of a product is the product of the moduli to write this as the modulus of the function evaluated, f evaluated at ci, which is this bit, the modulus of that, times the modulus of this bit, which is g evaluated at ci minus g evaluated at di. So that comes from that bit. Plus, and I've done the same thing here, we've got sum from I is equal to 1 to n delta xi times, and then we've used the fact that the product of the modulus of the product is the product of the moduli, to write this as the modulus of g evaluated at di times the modulus of this bit, f at ci minus f at di. time now for some more inequalities. So we want to eliminate this bit here, the mod of the function f evaluated at ci, and this bit here, the mod of the function g evaluated at di. Because if we could get rid of those bits, look what we'd be left with. Delta xi times this and delta xi times this. Those are those beautiful sums again for just the functions f and g alone. These types of sums, so we know something about what they're bounded by. They're bounded by the difference between the upper Riemann sums for the functions f and g, which is something we know something about because we know the function f and g are Riemann integrable, and therefore that we can make those differences between upper and lower sums indefinitely small. So that's where we're heading with this. So we want to get rid of these bits. What we know is that the function f and g are Riemann integrable over the interval ab. Now that means that they are bounded over that interval. If they weren't bounded, then they wouldn't be Riemann integrable. That's one of the things we proved in the first ever video on Riemann integration. So therefore there is some number such that the function is always modulus less than that value. So the function f then, the modulus of the function f, is always going to be less than or equal to some number that we'll call bf, for bound for the function f. So the function f over that interval ab is never going to take on a value that is greater than this or more negative than the negative version of this, so less than minus of this. Its modulus is always going to be within that bound. That's the meaning of the function f being bounded over that interval. Similarly, the function g is also going to be bounded over that interval ab because it is Riemann integrable over that interval. Therefore, we can conclude that there is some bg, some bound for the function g, such that the modulus of the function g anywhere on that interval ab is always less than or equal to this value. So let's start with the function f. So all of these values, ci's, for I is equal to 1 to n, they are all inside that interval ab. Therefore, the modulus of f of ci is always going to be less than or equal to this bound for the function on the interval ab. Now, of course, what we can do is really we have n inequalities there, because this is true for I is equal to 1 all the way up to n. For each of those inequalities, we can modify them by multiplying both sides by the things that we want in order to get the terms that appear here. So we'd be multiplying through by delta xi times the mod of g evaluated at ci minus g evaluated at di. So for I is equal to 1, you'd want delta x1 here, g of c1 minus g of d1. For I is equal to 2, you'd want to put in I is equal to 2 for everything. For I is equal to n, you'd put in I is equal to n for everything. So you'd modify these n inequalities by multiplying them by the relevant thing to get the corresponding terms over here. And those values that we're multiplying are positive values. This is a positive value and this is a positive value, so it's not going to change the sign of the inequality. So this side, when multiplied by that, becomes the term that we have here. This side becomes bf times delta xi times mod of g at ci minus g at di. And of course the next move is going to be to sum over I, because we have n inequalities here for each of the i's. So if it's the case that all of these things are less than or equal to all of these things, then if you sum all of these up over I is equal to 1 to n, it'll be less than or equal to the sum of all of these things over I is equal to 1 to n. So that gives us an inequality for this bit. Of course, we're now going to do exactly the same for this bit. So all these di's, they are inside the interval ab, and therefore mod of g di is going to be less than or equal to this bound for the function g over the interval ab. So you're going to have this inequality, and in fact this is n inequalities for all the different I values, and then you'll do the exact same trick as we did here. You're multiplying through by this times this, the relevant i's for each of the inequalities, and that will always be a positive number you're multiplying through by, because this is positive, so it's not going to flip the sign of the inequality. So you'll get something very similar to this from here, and then again you can sum over I is equal to 1 to n to get a similar inequality for this. And then of course if this is less than or equal to the sum of these, and this one is less than or equal to the corresponding sum for it, then overall the two things added together is going to be less than or equal to those two things added together. So the end result is what I've written down here. So this thing here is less than or equal to what we've got here. So just talking you through this. So this bit has now gone and been replaced by BF. And now we've pulled that out the front because it's a constant. So it's sum from I is equal to 1 to n, delta xi is still there, and then you've got this bit which is still here from here. So mod of g at ci minus g at di. And then you've done the same here, so you've got plus, you've got rid of this bit and replaced it with bg. It's a constant, so we've pulled it out the front. So bg times the sum from I is equal to 1 to n of delta xi, that's the same, and then this bit remains the same. So mod of f at ci minus f at di. So we can now conclude that this is greater than or equal to this, and this thing itself was greater than or equal to the initial sum, so by transitivity this thing is overall greater than or equal to the initial sum that we started with. But now look at these sums that we've got here, this sum here and this sum here. These are these types of sums that we've been studying this entire video. We've got our dissection and we're going over each one of the subintervals, multiplying the length of the subinterval by the modulus of the difference between the value that 2 points inside the subinterval are being mapped onto. And it's the same here. One is for the function g and one is for the function f. So they're no longer for the product of the two functions, they are sums just for the individual functions f and g. But we know if we took the set of all such functions for g and the set of all such functions for f, that those sets have suprema, and we know what the suprema of those sets are. The supremum for this thing's set is going to be the upper Riemann sum of the function g minus the lower Riemann sum for the function g, and for this one it's going to be the upper Riemann sum for f minus the lower Riemann sum for f. So because the suprema are upper bounds, the values of these specific sums must be less than or equal to the supremum of those sets. So this is hence going to be less than or equal to this value, the upper Riemann sum over our dissection d for g minus the lower Riemann sum over our dissection d for g. And this one is going to be less than or equal to this value, the upper Riemann sum for f minus the lower Riemann sum for f. Then, of course, all we've done is multiply those inequalities through by these positive constants, bf and bg, and then combine the two inequalities together to conclude that this thing must be less than or equal to this thing. So just to make sure this is crystal clear, I've written out these sets here. So if we took these sorts of sums for the function g and put them all into a set, that's the set we've got here. So all these sums from I is equal to 1 to n of delta xi times the modulus of the function evaluated at ci minus the function evaluated at di, where you're allowed to use any sequence of points c and any sequence of points d. If you put them all into a set, the supremum of that set is equal to this value, the upper Riemann sum minus the lower Riemann sum. Therefore, we have a specific example from this set here, so it is guaranteed to be less than or equal to this value here. Similarly, this thing is an element of this set here, so this is the set of all such sums for the function f now, where you're allowed to vary your sequence of points c and your sequence of d points. And again, the supremum of that set is going to be the upper Riemann sum for that function f minus the lower Riemann sum for that function f. So we have a specific example from this set here, so it is guaranteed to be less than or equal to this thing here. So we know that this thing here is less than or equal to this thing here, and this thing here is less than or equal to this thing here. BF and BG are both positive numbers, so we don't need to worry about anything strange happening. So this times this plus this times this is going to be less than or equal to this thing times this thing plus this thing times this thing. Now, this thing here itself was greater than or equal to the original sum that we started off with, which I've actually copied out down here. So because we know that this is less than or equal to this, and this is less than or equal to this, then by transitivity we know this is less than or equal to this. So our original sum that we started off with is less than or equal to this thing that we've ended up with here. Now, note we started off with one of these general sums, so this could have been any choice of C points and any choice of D points. Whereas the thing that we've got on this side now has no reference to the C points or the D points whatsoever. So actually, for a given dissection and given functions f and g, this is a constant. It's not varying with the C points or the D points. Also note that our derivation of this inequality did not put any requirements on the sequence of C points or the sequence of D points, apart from, of course, that they're in the correct subintervals, but that's part of the definition of the C and D points. So actually, for any choice of C points and D points, you would be able to derive this inequality, and hence, it's actually true that this value is greater than or equal to any one of these sums. Hence, it is actually an upper bound for the set of all of these sums, and since the upper Riemann sum minus the lower Riemann sum of the product function fg is the least upper bound of that set, we can therefore say that this value must be greater than or equal to that least upper bound value. So this then is the inequality that all of this work has been to get, that the upper Riemann sum over our dissection of the product function f times g minus the lower Riemann sum over our dissection of the product function f times g is less than or equal to the bound for the function f times the difference between the upper and lower Riemann sums of the function g alone over the dissection d, plus the bound for g times the difference between the upper and lower Riemann sums over this dissection of the function f alone. Now note, we know the function f and g are both Riemann integrable over the interval ab, so we know that we can make these things indefinitely small, and hence that's going to be the reason we're able to make this indefinitely small, because these are just constants after all. So if we can shrink this one indefinitely small and shrink this one indefinitely small, these are just constants. That means that overall this thing can shrink indefinitely small, and hence we're going to be able to prove that this must be able to shrink indefinitely small.